Welcome dear learners. We are continuing Unit 2 Chemical Bonding and Molecular Structure. In the present module we are discussing atomic orbital overlap. The contents of this module are here. First of all, concept of orbital overlap, conditions for effective overlap, SS overlapping, SP overlapping, PP overlapping, sigma and pi bonds, concept of covalency and variable covalency and maximum covalency. First of all, we are discussing concept of orbital overlap. Atomic orbital overlap refers to the interaction of atomic orbitals from two different atoms leading to the formation of a covalent bond. According to the valence bond theory concept, a chemical bond is formed by the overlapping of half-filled atomic orbitals. So what do you mean by the term overlap? Overlapping simply means the merging or combination of two different atomic orbitals. This atomic orbital overlap is very essential, and an idea of atomic orbital overlap is very essential to discuss every theories, the formation of covalent bond, the stability of the covalent bond, the bond strength, etc. etc. So, if atomic orbital overlap is more effective, then you can say that the covalent bond formed between them is very strong. If the atomic orbital overlap extent is comparatively low, then the bond strength will be low. And we can define atomic orbital overlap by the second statement. The atomic orbital overlap is the partial merging of atomic orbitals which results in pairing of electrons. For example, if you are taking the formation of hydrogen molecule, each hydrogen has 1s1 electronic arrangement, or 1s orbital is half-filled in each hydrogen. During the formation of the hydrogen molecule between two hydrogen atoms, the half-filled 1s orbitals of each hydrogen merged together to form H2 molecule. Now, the extent of overlap decides the strength of a covalent bond. In general, greater the overlap, the stronger is the bond formed between the atoms. Now we are discussing the most important part of this module, that is condition for effective overlap. We know the fact that a covalent bond is formed by the overlapping of atomic orbital, especially half-filled atomic orbital. The extent of orbital overlap governs the strength of the bond. We know these two basic aspects. Now we are looking on under what condition the overlapping between two atomic orbital is maximum. Under what condition the overlapping is minimum. That is why we are focusing on condition for effective overlap. For a strong and stable covalent bond, the overlapping orbitals must meet the following requirements or following conditions. First one, proper orientation. In order for the overlap to be more effective, the orientation of the participating atomic orbital is an important concern. Proper orientation should be ensured. That is, the interacting orbitals must align properly for maximum overlap. The second condition for effective overlap is here, comparable energy levels. It should be noted that the participating orbitals should have similar energy levels for effective overlapping. That means, if two atoms participating in overlap are A and B, and their atomic orbitals has a huge difference in their energy, then the overlapping between the atomic orbitals of atoms of A and B will not be effective. So, the participating atomic orbitals have comparable energy levels. This is the third condition for effective overlap, that is same phase interaction. Being the same phase or the same phase interaction is the most important condition for effective overlap. Bond formation occurs when atomic orbitals are in the same phase or atomic orbitals have same phase. This condition is represented as in-phase arrangement and out-of-phase arrangement. We can enter into more details of such phase interactions in the coming slides. Optimal distance is another important condition for effective overlap. Too much close or too little distance, far away or very close distance between the atomic orbital reduce the efficacy of overlap. That is, for two orbitals to participate in effective overlapping, the distance between them should be some optimal distance. It should be so much long or so much short. Now we are discussing a very important area, that is positive, negative and zero overlap. We discussed certain conditions for effective overlap. I just pointed out that the phase, same phase is a very important condition for effective overlap. There are so many other conditions also, and the same phase is one of the most important condition. The participating orbital must be in same phase. Based on the phase arrangement, we can have three kind of overlaps. They are positive, negative or zero overlap. When orbitals of two atoms come close to form a bond, their overlap may be positive, negative or zero depending upon sign. The sign is a notation of their phase and direction of orientation of amplitude of orbital wave functions in space. You can study the concept of orbital wave function in your higher classes. We are now just focusing on the phase or sign of the participating orbitals to mention positive, negative or zero overlap. Positive and negative sign on boundary surface diagrams show sign or phase of orbital wave function and are not related to charge. Now you can say that whenever you represent a p orbital, one lobe is associated with a plus sign, other lobe is associated with a negative sign. These signs are not the charges, but they simply represent the sign of their phase. So, orbital forming bond should have a same phase or same sign and orientation in space. That is, for effective overlap, only like sign should merge, or like phase should merge, or similar phase should overlap effectively. This is called positive overlap. So, overlap between like signs or overlap between orbitals which are in phase is known as the positive overlap. Now, let us have a glimpse on positive, negative and zero overlap in some orbitals, especially the s and p orbitals. So, with the help of sign, we can determine the phase. So, by noticing the phase, whether it is between like signs or opposite signs, we can represent the positive, negative or zero overlap by taking s and p orbitals as representative. Positive overlap between two p-z orbitals are shown here. This is the first p orbital, which is associated with a negative sign as well as a positive sign. This is the case of the first p orbital or p-z orbital. The second p-z orbital just come to overlap with the first p orbital. I just said to you the fact that only like sign overlap will lead to positive overlap. Here, the positive part is overlap with the positive part of the second p-z orbital, and hence you can say that this is a positive overlap between two p-z orbitals. Now we are just going through the positive overlap between two px orbitals. These are the px orbitals. In this 2px orbital, they will overlap laterally. The first part is called end-to-end overlap. The second one is called lateral overlap. We can enter into details of lateral and end-to-end overlap in coming slides and coming modules also. For the sake of the interpretation of the phase overlapping, we are just taking this picture. So, These two px orbitals are shown here. The upper part represents a like sign of positive charge and the lower part represents the like sign of negative charge, and you know the fact that only the overlapping of the like sign or similar phase overlap leads to positive overlap. So, this is the positive overlap between two px orbitals. Now, we are representing the positive overlap between two py orbitals. The three p orbitals px, py and pz are in mutually perpendicular arrangement with each other. So, px orbital it is along x direction, py along y direction, pz along z direction. So, we already shown the positive overlap in two pz orbitals, two px orbitals, and this is the pictorial representation of the positive overlap between two py orbitals. The like signs overlap here. So, the like sign is like this, plus plus part will overlap, minus minus part will be overlapping. So, this is the positive or in phase overlap between two py orbitals. Positive overlap between a pz orbital and s orbital is also shown here. Pz orbital is associated with the two parts, a negative part as well as a positive part, which represents its phase. The positive part overlap with the positive part of the s orbital. So, this is a positive overlap. Now, we can take negative overlap or out of phase overlap. I mentioned the fact that opposite signs overlap are otherwise called out of phase overlap. We can take negative overlap between two pz orbitals here. So, the positive part of the first p orbital overlap with the negative part of the second pz orbital. So, this is the overlap between two orbitals which are not in phase, or this kind of overlap is called out of phase overlap or negative overlap, which is practically creating no effectiveness between no effective overlap. This is ineffective overlap. Negative overlap between two px orbital can be represented like this. In the previous case, we just mentioned the positive overlap. Whenever I said about the positive overlap, only like sign will overlap. But in this picture, it is clear that positive part overlap with the negative part. So, this is ineffective. This kind of overlap is called negative or out of phase overlap. I mentioned you the fact that the sign represents the phase arrangement. Only like sign will overlap, that is called in phase or positive overlap. If the signs are opposite, they are called out of phase overlap or negative overlap. Negative overlap is totally ineffective. Now, this is the pictorial representation of negative overlap between two py orbitals. Here, positive part overlap with the negative lobe and vice versa, negative lobe overlap with the positive lobe. So, this is also out of phase or negative overlap. Negative overlap between pz orbital and an s orbital is also shown here. The negative part of the pz orbital overlap with the positive part or positive lobe of the positive part, only positive part, because s orbital is spherically symmetrical. So, this is the overlap between a negative part and a positive part, or this overlap is simply the out of phase overlap. So, we mentioned about the case of positive overlap and the negative overlap. There is one more overlap, that is nothing but the zero overlap. The zero overlap, it is out of phase due to different orientation direction of approach. A zero overlap is shown here. Here you can see that the p orbital is having a dumbbell shape and s orbital is spherically symmetrical. The position of the spherically symmetrical s orbital is at the center portion of the dumbbell, and hence there is no effective overlapping. So, another zero overlap is between px and py orbital. Px orbital pointed along x direction, py orbital pointed along the y direction. So, they are mutually perpendicular. Since the participating orbitals are mutually perpendicular, they are not in phase and there is no effective overlap. Such an overlap is called zero overlap. So, with the help of examples, we have demonstrated three kind of overlap: positive or in phase overlap, negative or out of phase overlap, and zero overlap. We also studied the various conditions for effective overlap. Now, we are selectively focusing on some certain atomic orbital overlapping. First of all, we are considering SS overlapping. In this case, there is overlap of two half-filled s orbitals along the internuclear axis. So, SS overlapping, as the name indicates, is the overlapping between two s orbitals. In order to get a covalent bond formation, the participating orbitals must be half-filled. So, SS overlapping can be considered as the overlap of two half-filled SS orbitals, probably along the internuclear axis. The SS orbital overlap or SS overlap is shown here. This is the first s orbital. The second s orbital is also shown. Overlapping simply means the merging of the atomic orbital. So, SS overlapped arrangement is shown on the right hand side after arrow. The overlap is spherically and symmetrical, is spherical as well as symmetrical, forming strong sigma bond. We can illustrate SS overlapping by taking hydrogen molecule formation as an example. Each hydrogen atom has one s orbital. When they come close together, their one s orbitals overlap to form a single bond between the single bond or sigma bond between the two hydrogen atoms. This is the illustration. This is the first hydrogen atom which is having half-filled one s arrangement. The second also hydrogen having similar one s half-filled arrangement. They will overlap through SS orbital overlap, and that overlapping lead to a single bond formation between the two hydrogen atoms. So, this clearly depicts the SS overlapping in hydrogen molecule to form hydrogen single bond hydrogen. Now, we are discussing the second kind of atomic orbital overlap, that is nothing but sp overlapping. In the case of sp overlapping, one s orbital and p orbital is overlapping together. This type of overlap occurs between especially half-filled s orbital of one atom with the half-filled p orbital of another atom. This is the pictorial representation of the sp overlapping. Here you can see the spherically symmetrical arrangement of the s orbital and dumbbell arrangement of the p orbital. There is effective sp orbital overlapping which enable the formation of a bond between the atoms. This sp overlapping can be illustrated by taking hydrogen fluoride molecule as a representative example. The 1s orbital of hydrogen overlaps with the 2p z orbital of the fluorine to form a sigma bond between hydrogen and fluorine as shown here. This is the 1s orbital of hydrogen which is half-filled. This is the 2p z orbital of fluorine which is also half-filled. There occur overlap between s and p orbital, or sp overlap happens here, leading to the formation of HF sigma bond. Now we are discussing pp overlapping. As the name indicates, here there are two p orbitals, they are going to overlap, and that is termed as the pp overlapping. This type of overlap takes place between, as I mentioned earlier, it occurs between half-filled p orbitals. This type of covalent bond takes place between half-filled p orbitals of the two approaching atoms. This is the symbol representation. The first p orbital combines with, overlaps with, merge with the second p orbital, leads to effective pp overlapping as shown in the right hand side. We can illustrate the pp overlapping by considering the formation of fluorine molecule as an example. The 2pz orbital of one fluorine atom overlaps with the 2pz orbital of other fluorine atom to form a sigma bond. This sigma bond formation is shown here. This is the half-filled 2pz orbital of the first fluorine. This is the half-filled 2pz orbital of the second fluorine. They will undergo pp overlapping to form F single bond F by the electron pairing, or FF bond formation happens through pp. Sigma and pi bonds. The covalent bond may be classified into two types depending on the type of overlapping. They are the sigma bond and the pi bond. I just mentioned about the fact that there are different kind of overlapping, end-to-end overlap or lateral overlap. Whenever I mentioned about the positive overlapping, I just shown about these parameters, and we are now entering into more details of the end-to-end overlap, lateral overlap, etc., which enable the formation of sigma bond and pi bond. Or we are now giving emphasis to two kinds of bonds, namely the sigma bond and the pi bond. First of all, sigma bond. This type of covalent bond is formed by end-to-end or head-on overlap of bonding orbitals along the internuclear axis. This is called head-on overlap or axial overlap. We can consider the formation of hydrogen, hydrogen fluoride and F2 molecule as depicted here in the first picture, second picture and the third picture. The first one shows formation of H2. Here there occur end-to-end overlap between two 1s orbital lead to hydrogen single bond hydrogen, that is a sigma bond. The second picture represents the sigma bond formation in HF molecule, that is also due to end-to-end overlap of s orbital and a pz orbital. Similarly, in the case of F2 molecule, there occur a sigma bond formation between two fluorine atoms by the end-to-end or head-on overlap between two half-filled 2p orbitals as shown here. So, we can conclude that a sigma bond is formed by the end-to-end overlapping of or head-on overlapping of participating atomic orbitals. Now we are focusing on the second type of bond, that is nothing but the pi bond. In the formation of a pi bond, the atomic orbitals overlap in such a way that their overlapping axes remain parallel to each other and perpendicular to internuclear axis. The orbitals formed due to sidewise overlapping consists of two saucer type charged clouds above and below the plane of participating atoms. This is a picture that clearly depicts the lateral or sidewise overlap. We can illustrate the formation of the pi bond by considering O2 molecule as a representative example. When half-filled 2p z orbitals of two oxygen atom overlap along z axis, practically we are taking z axis as the molecular axis, a sigma covalent bond is formed. Other two half-filled 2p y orbitals of two oxygen atoms overlap laterally or sidewise to form a pi bond. That is, the pi bond formation in oxygen molecule can be represented like this. For first oxygen atom, the configuration is 2p x2 2p y1 2p z1. The sigma bond formation happens between two half-filled 2p z orbitals. At the same time, a pi bond formation occurs between two half-filled 2py orbitals as depicted here. So, a sigma bond is formed by end-to-end overlap and a pi bond is formed by lateral or sidewise overlap of participating atomic orbitals. Now we are focusing on strength of sigma and pi bonds. The strength of a bond depends upon extent of overlapping. This point is very clear to you. In the case of a sigma bond, the overlapping of orbitals takes place to a larger extent. Hence, the sigma bond is stronger as compared to pi bond, where the extent of overlap occurs to a smaller extent. So, we can conclude that sigma bonds are stronger than pi bonds. Now, we are discussing the concept of covalency. Covalency refers to the number of covalent bonds an atom can form by sharing electron pairs with other atoms. That is, covalency represents number of covalent bonds that can be formed from an atom. The covalency depends on number of valence electrons available for bonding. Atoms achieve a stable electronic configuration, usually octet or duet, through the covalent bond formation. we can illustrate the concept of covalency by taking some examples. Hydrogen, it has only one valence electron, so it can form a single bond, so it is said to be monocovalent. Halogens have 7 electrons in their valence shell. They can attain octet by getting one more electron, so their covalency of halogen is also 1, or they are said to be monocovalent. At the same time, even though there are 6 valence electrons around the oxygen atom, it is requiring 2 more electrons to complete octet, so it can form 2 covalent bonds, so oxygen is said to be dicovalent. Similarly, nitrogen is tricovalent, and the most common example, carbon, which is nice illustration of tetracovalency, or carbon shows tetracovalency, or carbon atom is said to be tetracovalent. Factors affecting covalency is another point of discussion here. There are several factors such as valence electrons, hybridization, availability of empty orbitals, etc. will govern the covalency of an element. Now we are discussing variable covalency and maximum covalency. These are two important related concepts with the covalency. You know the fact that covalency represents the number of covalent bonds that can be formed from an element. Now what is meant by variable covalency? Variable covalency occurs when elements can exist more than one covalency depending on the compound it forms. This happens due to the availability of vacant d orbitals which allow elements to expand their valency. Transition elements and p-block elements commonly show variable covalency. Elements can promote electrons to higher energy orbitals, increasing the number of unpaired electrons for bonding. For example, phosphorus usually has a covalency of 3. For example, the PCl3 formation. But it can excite an electron to form 5 covalent bond, that is PCl5. So, phosphorus can exhibit common covalency of 3 and a higher covalency of 5. This is possible due to excitation of electrons. These are some examples for variable covalency. Phosphorus can show covalency of 3 in PCl3, covalency of 5 in PCl5. Sulfur can exhibit a covalency of 2 in H2S, covalency of 4 in SO2, and covalency of 6 in SF6. So, phosphorus and sulfur are nice examples for elements that exhibit variable covalency. And another concept, that is maximum covalency. Maximum covalency is the highest number of covalent bond an atom can form. It depends on the number of available valence electrons including s, p and d orbitals. Elements from third period onwards like phosphorus, sulfur, chlorine can show expanded octet and have a higher covalency. Second period elements like carbon, nitrogen, oxygen, fluorine cannot exceed covalency of 4 because they lack d orbitals. These elements have no d orbitals and they cannot extend their covalency above 4. Third period elements and beyond, phosphorus, sulfur, chlorine, etc. can have expanded valency due to the presence of vacant d orbitals in them. So, transition metals exhibit variable and maximum covalency due to involvement of d orbitals in chemical bonding. Some examples are here. Sulfur has a maximum covalency of 6, example is SF6. Phosphorus has maximum covalency of 5, that is in PCl5. So, we learned about the concept of covalency, variable covalency and maximum covalency as the last part. That's all about this complete module. Have a nice learning experience. Thank you.